Hello and welcome back to Math 121. This is section 4.2. We're going to be talking about logarithmic functions. Okay, so I want to talk about what a logarithm is. All right, and what I want you guys to do is I want you to solve the following. Okay. Let's think of this. Let's think of, 4 to the what power equals 16, okay? Given that exponential equation, we want to solve for x, okay? And so what I do here is I go, okay, well, if you just think intuitively, 4 to the second power gives me 16, so x is equal to 2, okay? What about this one? What about like 2 to the what power gives me 8? Okay, 2 squared is 4, but if I multiply it by 2 again, I get 8. So 2 to the third power, x is equal to 3. Okay, and if I take, say, like 8 to the x power gives me 64, all right, we're going to get that x is equal to 2. All right. And so these problems we can solve just by thinking about them. Okay. However, the question remains is, how do I solve, say, something like this where it's like 4 to the what power is equal to 7.82? Okay? Solving this equation cannot be done by using, just your brain and just thinking about it, okay? We need to come up with some sort of method to solve. Okay, so we need a method to solve. So need a method to solve. Okay, and what we want to use is we want to use a logarithm. Okay, so a logarithm solves for an exponent. All right. All right, and so what I want to do is this. All right, if I wanted to solve this equation for x, okay, I would rewrite this as log base 4 of 7.82 is equal to x. Okay, and we're going to talk about how you can plug this into your calculator. In Desmos, I want to say you can just plug it in as you see it, but that's just something that we can do. So let me do that just real quick. And what I end up getting is that x is equal to about 1.483. So 1.483. And so what we have to think about is this value is the exponent that makes this equation true up here. All right. So if I were to take, say 4 to the 1.483 power, that would give me 7.82. All right, so the whole point of a logarithm is to solve for an exponent. Okay, that's the idea. All right, so what we want to do is we want to write out, going from exponential form, so exponential form to logarithmic form, logarithm form. All right, and so what I want to do is this. Let's just say I have b to the x is equal to y. Okay, this is an exponential form. Okay, but if I wanted to change this into logarithm form, okay, then I would do this. I would say log base b of y is equal to x, okay? And what this does is this logarithm isolates my x value, which was my exponent over here, okay? So this is logarithm form, all right? So what I need to do is be able to go given exponential form, I need to be able to write something in logarithm form, and vice versa. I should be able to take something in logarithm form to write it in exponential form, okay? So the way I think about it is to go from exponential form to logarithm form. I say, okay, log base b, I'm solving for, you know, my exponent here, okay? I'm isolating my exponent, all right? But I'm taking the log of base b, all right? This little number here, when I say base b, remember over here, this is your base, this is your exponent, okay? So log base b of y, okay, and y is the result of raising b to the power of x, and that gives you x, okay? Now, if I wanted to go the other way, all right, so going from exponential form to logarithm form is pretty easy, but what I do to go from logarithm form to exponential form is a little bit different. And so what I'm going to do, so I'm going to write this, log to exponential. Okay. And what I think about is one of the ending scenes in Indiana Jones and the Last Crusade. Spoiler alert, this will kind of disclose the ending of the movie, so I hope you've seen it.
It's ours, Indy. Yours and
Okay, so the first thing I want to talk about is the fact that Elsa was explicitly told to not cross the seal by the knight, yet she does anyway. And then she drops it, this thing opens up, she attempts to go dive and catch it, yet, oh, come on! It's just unbelievable. I mean, I know Spielberg's great, but I've always wondered about that scene. This dive right here by Indiana Jones is great. Okay, so now, she's hanging up by Indiana Jones, okay? And she wants to get the Grail, all right? And she's really determined to get it. But then this happens.
Your other hand, honey, I can't hold you.
I can reach it. Reach it.
Give me your hand. Give me your other hand.
Okay. Look at where she goes. She just falls into this abyss. Now, one of the many questions that people often have with this movie scene is that, where does she go? Okay, how far down does this go? And, it's just kind of like this, all right, well, Elsa's just gone, all right, which is, it is what it is, okay? Like I said, spoiler alert. So Elsa falls into the abyss, okay? That's what I call it. Falls into the abyss, meaning we don't really know where it goes. It's just this cloudy figure here, in this crevasse, all right? So, thinking about that, here's how I use that concept to go from log to exponential, okay? And let's just think of a logarithmic problem, okay? Let's just say I have, log base 2 of 8 is equal to x, okay? So what you have is you have this logarithm, okay? And log is being supported by this little 2. And when I think of this little 2 supporting the log, and it's going, log has 3 letters, it's got a lot of baggage, it's really heavy. I'd rather just go over here and support the x, okay? So what happens is that the 2 moves over to the other side, the log drops down and falls into the abyss, much like how Elsa also falls into the abyss. Okay, and so what's left over is you get 8 is left over, and that's equal to 2. Now 2 is now supporting the x, and so x is my exponent. And so what I have done is I have gone from logarithmic notation to exponential notation, okay? So we should be able to do both. Go from exponential to log, and then log to exponential, okay? And so remember, I always just think about, the 2 is supporting the log, okay? It's sick of supporting the log. It's got a lot of drama. It wants to just go over and support the x, and the log drops down into the abyss, much like Elsa's demise in the ending scenes of Indiana Jones and the Last Crusade. But I digress, okay? So long story short, what I want to talk about is a little bit more about what an exponential function is. An exponential function, or I'm sorry, a logarithmic function is the inverse of an exponential function. So a logarithm is an inverse to an exponential function. Exponent. Okay? And so what you have to think about is the word opposite. Okay? And remember, when we're solving equations, what's the opposite of addition? That would be subtraction. Okay? What's the opposite of multiplication? That would be division. All right? What's the opposite of squaring something? Okay? Where you know what the exponent is. That would be taking the square root of something. Okay? But then we think about this, and it says, okay, well, what's the opposite? B to the x is equal to y. What's the opposite of raising something to an exponent? Okay, where you don't know what the exponent is, and that would be taking a log. So log base b of y is equal to x. Okay, so some pretty new stuff here. I do want to talk about the graph of a logarithmic function. Okay. So I'm going to come in here and let's graph a log function. Okay, and so what I have here, we first need to look at an exponential function. Okay, and I'm just going to look at the function y equals 2 to the x. Okay. And I've got a couple of points that I'm going to look at when I talk about an exponential function. So I've got x values and y values. Now I'm going to use the same 3 points to talk about what this graph looks like and what the log looks like. So I'm going to do this. I'm going to do -1, 0, and 1. Okay, now if I plug in -1 in for x, I'm going to get y equals 2 to the -1, which really gives me a 1 over 2 to the first. So this is a y value of 1/2. Okay, if I plug in 0, y equals 2 to the 0 power, that's just going to give me 1. Okay, always. Okay, and if I take y equals 2 to the first power, plug 1 in for x, I just get 2. Okay, so these points are always going to be on the graph. Okay, and I'm going to come over here and I'm going to graph these points. I'm going to do -1, 1, 1, and 2. Okay, and so if I graph these points here, and I'm going to graph these points here in red. Okay, and so I'm going to graph the point -1, 1/2 is right here. I'm going to plot the point 0, 1. And then I'm going to plot the point 1, 2. Okay, so if I plot this point, I get an exponential function that looks like that. Okay, now, what I want to do is graph the log function. Okay, so let's do this. Let's find the inverse of this function here. Okay, so if I wanted to find the inverse, okay, so inverse, I've got y equals 2 to the x power. Now, the inverse of that, remember, is I want to switch x and y, so I get x is equal to 2 to the y power, and I'm going to solve for y. In order to solve for y is an exponent, so I have to use a logarithm. So I would rewrite this as log base 2 of x is equal to y. All right. Now, this is my new function. This is my log function. Okay. So log function. All right. Now, in order for me to obtain the points on this log function, remember, what I did from this step to this step. I switched x and y. So in order for me to get the points of my log function, okay, which I'll write over here as y equals log base 2 of x, then I need to create a column for x and a column for y. Now remember what I did. I'm just switching these. So when and all I'm going to do is take the points from my exponential function, which we are able to generate, to obtain the points on my log function. So what I have here is this. I'm going to switch these two numbers. All right, so x is going to be 1/2, and the y value is going to be -1. I'm going to switch this so I get the point 1, 0, and then the point 2, 1. All right, and then I'm going to plot those points on the same graph over here. All right, so if I plot 1/2, -1, it's this point here. I'm going to plot the point 1, 0 here, and I'm going to plot the point 2, 1. So what I end up getting is the inverse function that looks like this, okay? And what I know is that these are going to be reflected over the line y equals x, okay? So that's what I have, all right? Those are the points on my graph. Now let's talk about something. Let's talk about the domain of my exponential function. Okay, my domain of my exponential function was all real numbers. Okay? And in interval notation, I would say that goes from -infinity to +infinity. Okay, my range on my exponential function is going to be that y is going to just be strictly greater than 0. Or I would say that we go from 0 to +infinity. Okay, and we talked about that a little bit in the last one. Okay, but remember, to find the domain and range of a log function, we switch them. Okay, and so my domain is now that x is just greater than 0. Okay, and then we go from 0 to +infinity. Okay, if we're talking about the range of my log function, we're going to have all real numbers. Okay, or I would say that goes from -infinity to +infinity. All right, and that's all we're doing. Okay, and so that right there gives me, what I've got. So when I think about this, okay, when I write out my log function, I'm going to write this out, y equals log base 2 of x, okay, then what I need to keep in mind here, remember our domain. Our domain is that x is greater than 0, okay, so whatever's inside of here, okay, if we want to find the domain, we have to set that greater than 0. Okay, because that's what our domain is. All right, now we can shift things, we can move them around and do compositions of these, but for right now, we're just going to leave it like that. Okay, now the next thing I want to do is look at evaluating logs on the calculator. Okay, so let's do. Let me come in here, and we're going to evaluate logs on the calculator. And what I do is I do this thing called the change of base. So if I wanted to calculate, say, log base 3 of, say 5, okay, and that would equal x. Now remember what this means. This means that I'm taking 3 to the x power is equal to 5. Okay, this, I don't know what that answer is. Okay, 3 to the what power is going to equal 5. I don't know what that is. Okay, so on something like this that you can't solve in your head, you need to use the change of base. And so what I would do, in the calculator, you have a log button. Okay, so I would do log of 5 divided by log of 3. Okay, so this is what you put into your calculator. Now when I do that, all right, let me do log of 5 divided by log of 3, and I'm getting that x is equal to about, what is that, 1.465? 1.465. Okay, so to solve those, that's what you would do. okay? Now, the next thing I have is called a natural log, okay? So this is a natural log, all right? And what I'm going to do here is think of the equation, say y equals e to the x, okay? We're back to that using that number e, all right? And so this is a naturally occurring number, hence why we're going to call this a natural log, okay? And so what I want to do is this. I want to turn this into log form. So what I do is I switch and create a natural log function, all right? So what I would do here is I would do this. I would switch x and y. So I'm going to get x equals e to the y power. And what I'm going to have is I'm going to now apply the logarithm portion to this. And so I'm going to say log base e of x is equal to my exponent y. Okay? So when I write out y equals log base e of x, that's a lot. Okay? This is a natural log. So what we use is the notation y equals ln of x, okay? These two things mean the same thing, okay? And same thing goes. If I'm trying to find the domain of this, it's going to have the same idea. This domain, x, is going to be greater than 0, okay? So you're going to be asked to do those kinds of things, all right? So that's about all I got for this video. Let's go ahead and get started on the rest of these problems, and we'll talk to you soon. Thanks a lot. Bye.